Earlier in the semester, I talked a little bit about differentials like dy dx, Leibniz notation, and what some of those things mean. In this video, I wanted to get back into the notation a little bit more, talk about delta notation and differential notation, and kind of get at those ideas on a little bit better level. But basically, another way we could write a marginal cost function is by using delta notation. And notation you've probably seen before, and I wanted to kind of connect those back to a lot of the notation that we've used for derivatives so far. But basically, like, for example, when we are talking about the slope, sometimes we write that as the delta y over delta x, which you've probably seen before, or, rise or run, which refers to the difference in y, or the change in y divided by the change of x. Like, as we're looking at the slope of a secant line between 2 points, that's equal to the ratio of the change in y, or, looking at it as a difference quotient, f of x plus h minus f of x is the change in height, all divided by h. This gives us the slope of the secant line, and this gives us, we can see it as that particular ratio using calculus, the way we do it in calculus. But, at the end of the day, it's the same as y2 minus y1 divided by x2 minus x1. Just we've changed the variables to match our difference quotient. And as we know, if we take the limit of the difference quotient, the limit as h approaches 0, these get closer and closer together, and it gives us the slope at a particular point, the tangent line, which again is the point of derivative slope function. Anyways, this is just a different way of writing the exact same thing. And if we kind of change these things, we could also write delta y as f of x plus delta x minus f of x. Because, like, at the end of the day, if you can see, h is just equivalent to delta x. It's the same exact, the idea. It's how far is it from left to right? And so, basically, if we were to rewrite slope, we could write delta y as f of x plus delta x minus f of x, the change in those. Or again, writing it this way or that way. So let's look at an example. It says let y equal x squared. For x is equal to 3 and delta x equal 0.1, it says find delta y. So at the end of the day, we have a curve, and we want to know as x changes, what happens with y. But essentially, we could use these sorts of formulas and so forth in order to do this, but let's just go ahead and apply this original formula up here, because we have our function, which is x squared, and if we want to know what is delta y, let's see, I'm on the wrong page on my tablet. Delta y is equal to f of x plus delta x minus f of x. Or plugging in what I was given, we have x is 3, delta x is 0.1, and x is 3. So what this is essentially asking is, what is f of 3.1 minus f of 3? Or, in the context of derivatives, this is, at the end of the day, finding basically the numerator of the average rate of change. What is f of b minus f of a, based on the context of this problem? And I would use the function x squared. So I would have, this is equal to 3.1 squared minus 3 squared. We can go ahead and do that. 3.1 squared minus 3 squared. And that would leave me with approximately or exactly 0.61, which would be delta y in this particular case. And why this is relevant is, it's just sort of a different way of writing things, is the idea of a differential and why that comes back to the original notation as Leibniz wrote it. But like when we say dy dx, if you remember how I said this before, is this represents the derivative of y with respect to x. That's typically how we say dy dx and kind of its meaning. But each actual individual component of a differential technically has its meaning, to which is defined below. What does dx mean by itself, and what does dy mean by itself? But if we sort of examine this on a basis based on the definition of the derivative, we have right here, this is just a difference quotient where we've changed h to delta x. As I said, those are the same, right? Because this is f of x plus h minus f of x divided by h, and the limit as h approaches 0. But, if we change it to delta x notation, we would get this. Or more compactly, we could just say this is the limit as delta x approaches 0 of delta y over delta x. Or again, exactly, we have our slope formula as the change in x gets smaller, as written using the delta notation. And like at the end of the day, that's what dy dx means. It's kind of like the infinitesimal limit of the change in x over change in y. And that's really what how I envision what a differential is. Delta x means the actual difference in this point in time. Dy dx is kind of like the limit. It's as close as you can get on an infinitesimal scale about the change in y over the change in x. And also another thing that we can conclude from this is that, again, kind of applying the ideas from the last video, is that dy dx is approximately equal to delta y over delta x when delta x is small. Because like with the idea of marginalization, the point of marginalization is that if we use a derivative to predict another value, it should be pretty close to correct because the derivative is so close to the line, right? A tangent line correctly models the slope at any point in time. And if you extrapolate, and again, as long as you don't go too far away, like if I was to go super far away on this line, it would divert from the actual cost pattern of the, but like when I'm nearby, it's essentially indistinguishable from the line or very, very close. And that's kind of what this is saying, that and again, that was actually applying the value of the function, whereas this is just saying the slope, the exact slope at a point in time is approximately equal to, it's sort of like saying the tangent line is almost the same as the secant line if we're dealing with close by intervals. And this graph kind of helps cement that idea that if we have an actual curvature to our function, the tangent line is pretty close. And this graph also helps us see a little bit more about what those things mean. And in the context of differentials, let's go ahead and define them now. It says for y is equal f of x, we define dx, called the differential of x, by dx is equal to delta x. So essentially there is no meaning, there's no difference in meaning behind what dx is. It is just delta x. But dy is a little bit different. It's called the differential of y by dy equal f prime dx. Or what this is saying is I take the derivative and multiply by delta x in order to get dy. And this is definitely something that can be a little bit confusing. But another way to sort of understand the algebra behind this idea is if I divide both sides by dx, because technically differentials you can work with on an individual basis. It's not just a combined fraction. But usually we just think about dy dx, that just means derivative of y with respect to x, which it does. But sometimes you can actually solve differentials. And they're useful in certain times without needing to complicate ourselves with the idea. But if I just divide by dx on both sides, what that would leave me with is dy dx is equal to f prime of x. And this is something which I said earlier. They're the same. They mean the same thing. They're the derivative of the function at each point in time. But it's just sort of another way of reorganizing this. Or imagine multiplying both sides by dx. That's one way you could remember how a differential is defined to be. And so let's look at the graph because this makes more sense. Like dx and delta x, those are the same thing. They mean this width here. But the difference between dy and delta y, notice that dy is the change, like again, if we look at dy dx, that's the slope of the tangent line. So the tangent line is a little bit different from this, where delta y and delta x is the slope of the secant line, and they're a little bit different. And if we wanted to know, well, what is dy? Basically, we just need to take your derivative and multiply by dx because it would give you the actual value at that point in time. So it makes a little bit of sense about this. And kind of summarizing this in a note, delta x and dx mean the same thing, but delta y and dy, they are not the same thing. Though, kind of again using this idea over here, since dx and delta x mean exactly the same thing, we could kind of conclude, well, dy is approximately equal to delta y. And by looking at the graph, notice that dy is a particular height value. It's pretty close to that of delta y. And again, this is the idea of marginalizing. We're using a derivative to predict the value. It's kind of like the difference between the actuality of delta y and dy itself. And also, what this one says right here is kind of, again, an extension of a differential. Delta y is approximately the derivative times delta x. This is the exact same idea from marginalization. But anyways, let's look at an example. It says let y be equal to x times 2 minus x quantity squared. It says find dy and find dy when x is equal to 4 and blah, 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 and compare to delta y. But basically, if I wanted to find dy, I could just use this formula, or I could just figure out, well, what is dy dx, and then multiply through by dx. So either way is fine, but let's just start by finding the derivative. So here, I could use the product rule, or I could multiply it out. I think it might make more sense just to take the original function and multiply it out. This would be x times, if I need to square something, I could always use a shortcut which is square the first, multiply the inside 2 by 2, and then square the second. But basically, if I were to, remember this is a square, I need to FOIL this, and that would FOIL to make this polynomial. Then multiplying by x would give me 4x minus 4x squared plus x cubed. And that's, again, just sort of expanding that so that I don't have to use any other rules. Now I could just use the power rule. My derivative, if I were to reorganize, derivative of x cubed would be 3x squared. Then derivative of negative 4x squared is negative 8x, and derivative of 4x is just 4. So I get my derivative function here. And if I just want dy, the point is I can multiply through by dx to figure out what is the differential. And the meaning is very similar to delta x. Because dx and dx is the same as delta x, dy is similar to delta y. Or just kind of gives us the change in, if we want to know just the change in y, it's the value of the function times the change in the function at that point in time. It says find dy when x equal 4 and dx equal to 0.1. But basically, I just plug those things in. Dy would be equal to, well, let's plug, again, 4 in for x. So I'd have 3 times 4 squared minus 8 times 4 plus 4. And that's my parentheses. And that would give me 20. And then dx is just as 0.01. So 0.01 times 20 should be 0.2. And that would give me the value of my differential for this particular position on the curve. And again, I could kind of imagine it with a graph or so forth. But another point is this should be relatively close to delta y, which is just a little bit different. And if I want to know delta y, I could do exactly what I did up here in order to find that. It's just a change in y over that particular parameter. So again, if we use that formula, delta y is equal to, well, let's just go back up here, fx plus delta x minus fx. So it would be f of 4.01 minus f of 4. It's literally just the change in the height over the interval that we're talking about. And it's again, it's kind of the same idea. What's the approximated slope, not slope, but just rise, and then what's the actual rise over the stated interval. And so we already know f of 4, which is 20, but we don't know f of 4.1. So we'd have, again, 3 times 4.01 squared minus 8 times 4.01 plus 4. I just realized I'm using the derivative, which I don't want to do. So I made an oopsie up here because this is, oh no. I never mind. We don't know f of 4. I'm sorry. This, because we plugged in 4 into the derivative because that's what we needed to do there. So let me erase that. I need to redo both of these. I need to use the original function here because this is not f prime. Whereas this was because I had to differentiate it in order to get dy and dx. This doesn't involve derivatives at all. It's, again, like tangent line versus secant line, the whole comparison yet again. So sorry, this would be 4.01 times 2 minus 4.01 squared. And this would be f of 4.01, which would be 16.2. And I'll just go ahead and leave it at that because I could continue the rest of it. I'll just write 0.008. And then minus f of 4, same deal, I just want to plug in 4 only. So let's delete the 0.01, delete the 0.01 here, and that would give me exactly 16. And the difference there is not exactly 0.2, but it's pretty darn close. 16 minus 16.02008 would just be 0.2008. But again, the idea is that would be delta y given these parameters. Very, very, very close, a very approximate, especially when dx is really small. Like, when it's larger, there's going to be more variation from the tangent line. But at the end of the day, summary tangent lines can be used to approximate values. Same thing as from the last video, like with marginalizing. But it's just helpful to explore the notation dy and understand more of what that means. At the end of the day, it's your derivative.